Thank you, and good day, webinar participants. Thank you very much for taking time with us today. I hope you all are doing well today. Today I'm going to present us a topic, Introduction to Power Electronics Reliability. It is a topic that I strongly believe the dialogue between the industry and academics is essential. So I'm very grateful that Hyoki provides this opportunity to us for this webinar. In this webinar, we're going to discuss three main parts. The first part is about the application demands and the challenges from the industry perspective that we came across in the last 8 years. And then the second part will specifically discuss line examples that from our research. And the last part will look at the future. So what are the remaining challenges we're going to talk about? So in the remaining of the webinar, I'm going to mute my video so that without disturbing all of us with the video system. So just a moment. Okay. Before we go to the main part, I would like to give us a little background about our research environment and also the topic we have been working on. So in the Department of Energy Technology at Aalborg University, we mainly work on the production, distribution, consumption, and control of the energy, mainly from the renewable energies and then to different applications. So we could see that in this chain, we have different applications of power electronics. So that's why in our department, we have about 60% of the manpower that concentrate on the power electronics research and its relevant applications. Specifically on the topic we're going to discuss today, we intensively start this topic in 2011. At that time, we established the Center of Reliable Power Electronics that is founded by Danish government and also 4 major Danish companies together. So since 2011, our research is mainly divided into 2 parts. The first part is more fundamental research. So we build up research infrastructures. We work on topics that are common challenges, both scientifically, but also from technically from the application perspective. So especially we have this core project that is a research center. And then at the moment we work intensively on 3 major projects. The first one is this X-Power. This is to build up a national level power electronics reliability testing center. And also we work on the reliability of power electronics based power systems. So that is talking about multiple power converter systems for future modern power systems and microgrids, smart grid, and so on. And meanwhile, we also have continuous collaboration with industries. So that's why another important pillar of our research is about innovation and commercialization. We have been collaborate with different companies, as Oliver introduced. And also, meanwhile, we help our graduates to do startups and from the research result directly from the research here. So this is the background. So let's go to the main part. We're going to talk about the challenges beyond efficiency and power density. So in power electronics area, we know that in the last 5 decades, a lot of attention has been put how to improve the efficiency and also how to shrink the size of the power converters. Later, we discuss why we need also to look at reliability and consider the performance factor as efficiency and power density. First of all, I would like to just recap to us a brief introduction of what is power electronics. So basically, power electronics is an interface between the electricity generation and the consumption. So this could be bidirectional. So power electronics itself does not generate any electricity, but it's process the energy, process the electrical energy, so that it can provide, for example, to provide electricity for different applications, or it can help to generate the electricity to help the generation of the electricity to our electrical grid, for example, to connect the wind turbines, to connect the PV panels to our electricity grid. In the last 5 decades, we see there are a huge number of architecture of power electronics that are talking about the circuit topologies, the control strategies of that. Those architectures have a function that either to change the voltage, to change the current or the frequency, so that it can fulfill the requirement. But no matter what kind of architectures, most of the power converters have, from the component perspective, have this different type of components. Like the essential part is this switching device. So this is the only component in a power converter that you can control. So you can control it on and off. Essentially, it's like a mechanical switch, like you press a button and then your lamp is on. If you switch it off, and then your lamp is off. But the difference of this power semiconductor switching is that it can be turned on and off very fast, from hundreds of times to millions of times per second. So this is the first important components in the power converters. And then we have passive components like capacitors, inductors, transformers, resistors. We call it passive because it cannot be controlled. So those components are also very important, like capacitors and magnetic components. They are served at a certain energy buffer. So they store energy when it's needed and they release energy, or when there is excessive energy, it stores the energy in the power converter. And then we have a controller, feedback control to control the on and off of this switching device. Power electronics becomes a discipline or defined discipline since 1970s. There is more clear definition of what is power electronics and become a discipline, and it becomes a program in universities. But actually, it has a very long history, more than 100 years. If we talk about the power conversion, here we divide it into 3 phases. So now we're in the phase 3, of course. And if we look at in the past, before 1957, before the invention of the thyristor, a lot of efforts are searching a switch elements. As I mentioned in the previous slide, that the switch is an important component that can be the only component that is controlled in a power converter. So before the invention of the semiconductor devices, the controllable semiconductor devices, people are looking for different ways so that they can find the element has at least 2 impedance states. One is an in-fleet impedance that is equivalent to off state, and one is almost 0 impedance that is corresponding to the on state. And after the invention of the thyristor, and until 2000, we see that there are a lot of efforts searching for circuit topologies, control, modeling methods, and try to push up the switching frequency, reduce power loss, and improving the gate driving technologies. And digital control becomes more and more popular. And then since early 2000, we see the power electronics research becomes more application oriented. So people talk about the packaging, people talk about the thermal management, and EMI, EMC, reliability, large-scale power electronic systems, modularization. So those challenges are more specific to different applications, So reliability is one of the things that is quite critical to some of the applications. So the development of power electronics, of course, is quite dependent or affected by the advancement of power semiconductor technologies. So if we look at here, since the invention of the thyristor, so in 1980s, 70s, there is a power MOSFET, and then there's IGBT later. And nowadays, we all know that this wide bandgap device is becoming a hot topic and also offers great promising potentials to the application of power electronics. So the development of the power semiconductor technologies will advance the power electronics technology itself. So this is some background. And then along the years, we see there is increasing use of power electronics. So the majority of the electricity today are processed by this power electronics interface, either from the utilization side or from the generation side. For example, this is one of the example for the transportation application. This is a conventional power conversion system, like we have a line frequency transformer, and then we have a full quadrant converter to convert the input that is AC, either like 15 kilovolt, 16.7 hertz, like in Europe, and in some other countries it's like 25 kilovolt, 50 hertz, and then to convert it into a conditioned AC to drive the traction motors. So in this conventional architecture, it's still dominantly used, of course, and one of the bottleneck is this line frequency transformer. So this transformer is bulky and heavy. We know that for this e-mobility application, the size and the weight are critical performance factors. So people think about whether we can replace this line frequency transformer by power electronics converters. So this is what we call solid state transformer, or we call power electronics transformer technology. So by replacing this line frequency transformer by power converters, it has it potentially reduce the size and also the weight of this the overall system. So in this way, this is just one example that power electronics converters is increasingly used to replace some other system like mechanical systems or low frequency transformers for that. This is one example from ABB. For example, they propose this system to replace the line frequency transformer. So this is a prototype from them. And also below is a example from Mitsubishi that uses latest generation of semiconductor device technology, the full silicon carbide traction inverters, just to give some examples. And not only on the utilization part, but also from the energy generation side, we see an increasing use of power electronics. One example is the wind turbine converters. Nowadays, wind energy becomes one of the dominant energy source in our overall energy landscape. And in the early phase of the wind energy, either we directly connect it to the grid in the 1980s, the very early phase, or later we convert the the electricity generated from the wind turbine by a partial converter. So like 30% of the energy processed by the power converters. But here we can see there is a full-scale power converter. That means all of the energy generated by the wind turbine will go through a power converter and then to the grid. So there are a number of important issues in those applications, like we have to look at the reliability, we have to look at the efficiency, cost, we have to look at the grid code to fulfill the standard from different countries. So power electronics are increasingly used in different systems. And if we look at the performance factors, as I mentioned at the very beginning, in the past, we look at a lot on the efficiency and power density, especially at the power electronic engineer or researchers, we look at those. But then in 2012, we had a workshop with a few industry companies, and then we specifically discussed the reliability challenges. So at that time, from their perspective, we come up with this table. The reliability challenge from the industry perspective is that let's look first on the future. So in the future, the customer really needs a peace of mind. Like if they buy your products or a surface, they want it to run for the whole surface life without any trouble. And also, some of the application customers demand predictive maintenance. Predictive maintenance means to schedule the maintenance based on the conditions of the system or components, instead of like we do it regularly every 2 years or every 6 months, or talk about the years of warranty as what we did in the past. This is customer expectations. And then if we look at the reliability target, because systems have become more complex, even many systems become more easy to use, but to achieve this user-friendly features, maybe internally the hardware and software become more complex. And this means even for given system level reliability, at the component level, the reliability target becomes more and more stringent. So this really requires us to do at least 2 things from the R&D perspective. The first one is to update our design flow, the design methodologies. So to consider the reliability as a performance factor as early as possible in the product development process. And then we have to understand what are the actual user conditions. So how your customers will use the products in the field. What are the environmental and operational conditions? And as a researcher in university, one of the major research directions is to understand the failure mechanisms. So how those power electronics components could fail, what happens at the material level, and how we can design the components or design the systems to mitigate those issues. So these are the future challenges we see when we discuss with industries along the years. And we also see there are 2 trends. The first one is that the surface become more and more important, like especially like in renewable energy generation. The contract were signed maybe not only for the product, but also for the years of surface during the whole surface life. And while we try to look at the physics of failure, we also see that there's huge opportunity or potential that the data, collecting the data from the field operation becomes a trend, and also industries start to implement data collection systems, so that how to utilize those data in combination with the understanding of the physics of failure, it can create new opportunities. Yeah, as I mentioned, to consider the reliability performance as early as possible in the design phase, like from the concept and design phase, is very important, because in case there is any design defect that we haven't identified during this early phase, it will cause huge economic loss when it goes to the customer's hands. So that's why since 2011, at the Center of Reliable Power Electronics, we address research challenges and industry demands from 3 aspects. The first aspect is we do research on the component physics. So try to understand the physics of failure, the physics of degradation of key power electronics components. And the second aspect is to support the design and validation phase. That is the product development phase. And specifically, we look at how to integrate the design for reliability approach into the product development, so that we can provide, at the university, we provide models and tools, so that for industry, they can use those models and tools to estimate the reliability, to support the decision making during the concept and design phase. And after that, to look at the testing methods to do the robustness validation. And the third aspect is also very important, is when the product in the field operation, we still have the opportunity to ensure its reliable operation. That is, like, since the digital controller is a mainstream, so digital controller has a flexibility that we can update the control scheme. We can even change control parameters adaptively depending on the real-time operating conditions. So we can make the controller more intelligent to adapt to the situation so that it can optimize its performance during the operation. Another pillar in this aspect is the condition monitoring. So for the either reliability critical or availability critical or safety critical applications, if we can implement some condition monitoring method that can monitor the healthy status of key assets in the system, this will create value for some applications. So this is the main scope of our research. We do see some paradigm shifts, like from component to failure mechanisms. So instead of looking at only the component level, we can dig down to the inside the component and different failure mechanisms. And then from constant failure rate to the failure level with time, because the failure rate will really depends on the operating conditions, depending on in which stage in the whole surface life, from the reliability prediction to the overall robustness validation, and also from reliability to also the degradation. So in applications where failure may not be an option, we have to look at the degradation curve. We have to look at the process that how component will be degraded before its failure. So in this case, we can ensure that the reliable operation during the surface life. That's why in the second part of this presentation, I will share with us some selected examples from these three aspects of research. We start from the first one, that is to understand the failure mechanisms of power electronics components. So the example one here is try to understand the physics of failure of these IGBT modules. So the IGBT module shown here is widely used in wind turbine converters with 1.7 kilowatt 1000 N IGBT. One way we do the one direction research direction is to understand those failure mechanisms by simulation, because simulation tools nowadays are very powerful. So here we do the multi-physics simulation of this IGBT module, and one of the failure mechanisms is related to the temperature variation. So when temperature varies across different points of this IGBT, because there are interconnections between different materials. So each kind of materials have a certain thermal expansion coefficient. In this way, because they have different thermal expansion coefficient, for the same change of the temperature, there will be mechanical stress induced during the bond wire or the solder joint or the solder joint at the chip solder or the base plate solder. In this way, we do the simulation, and then we can simulate the deformation, the mechanical stress, the corresponding plastic deformation, and elastic deformation. So this is one way, one approach to understand the issue. And the second approach, of course, is to do the testing. So here we build up different testing setups, especially here we call the power cycling testing. So this is a DUT. So we use the power converters to generate those temperature variation. So we control this power converter so that it can achieve a certain level of temperature generation. So here, meanwhile, we supply the high voltage here. So it's to emulate the realistic operating conditions of this DUT for the voltage. And then we observe, usually we monitor the parameters. So this parameter we call the health indicator. So the change of these parameters is a good indication of the aging of these power converters. And at the bottom side is another setup, is a low power setup for the low power modules, 600 volt and 30 amp. So by utilizing those testing systems, we can perform the accelerated testing of those semiconductor switches. Beside this long-term testing in the previous slides, so we do the cycling for millions of cycles to emulate the degradation. We know that not only there is this kind of degradation, but also there may be some a single event related failure. So here is a setup that we perform the short circuit testing of the IGBT modules. And specifically here, we do the non-destructive short circuit testing because those power modules are very expensive. We don't want to fail it just one testing. So we can precisely control the short circuit duration. Like here is 5 microseconds. We can also control it like 6, 8, 20, 40, and so on with a resolution of 10 nanoseconds. So we can precisely control that. And then we can repeat the testing for many, many times to see what is the effect on those power modules. Beside the active device power semiconductors, we also perform testing for the passive components. Here example that we do the application-oriented degradation testing of capacitors. Here's a testing setup that we have chambers, we have power supplies to emulate the electrical stress, we have characterization equipment to measure those key health indicators. The uniqueness here is that according to the industry standard, there is no requirement on the humidity-related testing to the failure. So usually there's a qualification testing. Let's say you have to pass 500 hours testing at this humidity level, but it does not require that you have to test until the failure to know the effect of the temperature. So here we perform the testing to the failure so that we can find out the humidity derating factor. So how the lifetime will be dependent on the humidity here for these DC-link film capacitors. In the capacitor testing, we also have this, we call it capacitor bank characterization. So this is also application oriented because when we look at the capacitor data sheets or application notes from manufacturers, we see that usually there are parameters on the electrical part, or some manufacturers, they provide the thermal resistance. But for the, in the real application, like here, in this megawatt power converter application, for certain cooling conditions, actually those thermal impedance and capacitance, thermal capacitance are not known. So they will be changed depending on the cooling conditions. In those applications, sometimes it's there is a stringent cost constraint. So one way to do it is to design to the limit. So we try to shrink the demand on the capacitors to design to the limit with minimum but sufficient margins. In this way, we need much better model to support the decision making. So this is the setup that we can characterize the capacitor banks under realistic cooling conditions and to obtain the thermal capacitance and thermal resistance model. Magnetics is another type of important passive components. So here we also, we have implemented a characterization system that try to characterize the medial voltage, medial frequency isolation transformers at realistic operating condition. The system designed to test up to 20 kilovolts insulation voltage. And then we use this power analyzer from Hilke because this is very good to test up to 2 megahertz. So this is what the feature that we used here. And another example is go to the second aspect we introduced, the design for reliability. So in order to integrate this design approach into our product development procedure, we need the model. So what we call model-based design. So here at Auburn University, we have developed a software tool that is called Design for Reliability and Robustness. So this tool helps us to do a quick component level reliability or system level reliability modeling based on the environmental and operating conditions of the power converter systems. So we go through these 6 steps, and then we can go to obtain the component and system level reliability. So here's the approach we used. We called it the mission profile based reliability prediction. if you have ever done the reliability prediction, you may know that there are different handbooks in different industries, or a general one used widely is like this military handbook. In those handbooks, there are failure rate models and so on. You can get finally you can get a number based on those handbooks. But the question is that how realistic of those numbers? That's why in this way we call it, our approach is that we based on the real operating conditions. Let's say we collect long-term operating conditions for PV application or for wind application, for motor drive application, and then we do the modeling at the system level, at the power electronics converter level, and then at the component level. Finally go to the component reliability and system level reliability. So this is a software tool we developed. It has been applied to several industry companies' product development and validation. The third aspect, I will give two examples. The first one is a mission profile logger. As I mentioned, now you could see industry start to put more attention on the data collection. So here is an example of we call mission profile logger that is developed by us. So in this mission profile logger, we can measure the environmental conditions like the temperature, the humidity, but also we can measure some of the health indicators of power semiconductors. And those data will be stored in an SD card, and then it can transmit wirelessly to the computer. And we can, this is an example to show some of the inside and outside the temperature and the humidity inside and outside the cabinet. So this is a fit testing in Denmark in one of the small PV plants. We put those mission profile logger inside and outside the cabinet to collect this data. But this kind of measurement system becomes more and more interesting to be implemented. Of course, it will become smaller and smaller and cheaper for that. Another example is also for the condition monitoring. If we look at there are several like condition monitoring platform provided by companies and the different concepts for the prognostic healthy management and so on. So all of those platforms relies on the component level or the converter level measurements. So these are more fundamental technologies for that as an input for those platforms. Like in this converter level, we have proposed a method that help us to estimate the health indicator of those power semiconductor devices at the converter level. Because in the past, what people did is to add a circuit at each of these power device, And the practical issue is that usually for applications where the condition monitoring can create values, it's difficult for them to change the circuit design. Or for existing product, it's difficult to access those power devices. So here, what we propose is that we propose a converter level circuit. So what we need to do is just to connect these output terminals by a small circuit, and then we can get all of the health indicators of these 6 switches on that. So in this way, it provides the best accessibility to the existing and new products design. And also, we utilize some novel circuit architectures. The cost of this proposed circuit is just about 10% of the existing solutions. And this technology can be implemented into different forms. The first one can be as an IC chip. So that is embedded in the system so that to measure the on-state voltage information that is a health indicator of those semiconductor switches, or it can be as a voltage probe that can be used together with oscilloscope. Because this voltage probe can block the high voltage, like 1000 volts, and then precisely measure the low voltage in a range of few volts. It can also be integrated as hand carry instrument for the surface people to connect to the output of certain converters, and then to finally get the healthy conditions of those converters. So these are the line examples I would like to share with us. Now let's come to the third part, the outlook on the further scientific challenges and opportunities in the power electronics reliability research from our perspective. The first challenge is if we look at the system level application, we know that a power electronics converter system has both hardware, have software, so both the hardware and software could fail. And also we have human errors. We have installation error, we have transportation issues and so on. So all of those could create the failure. So there are multiple failure sources. And also the failure could be due to either the wear out, that is a long-term related issues, or the catastrophic failure due to the sudden effect or single event effect, when we call it. And in our research at the university, we mainly deal with the hardware reliability at the moment, at least, because our background is in power electronics, and then we're mainly dealing with wear out failure and catastrophic failure of key power electronics components like power semiconductors, passive components, PCBs, but there are some other components as well. So we could see that there are also multi-component issues. At the moment, we gain, I would say, good knowledge on the wear out failure, on the long-term degradation by testing, by simulations, and by prediction. But we still need to do more on the robustness to look at those catastrophic failures, the design margins, and how it will affect, and how to, the question is how we can select size the components that has a minimum design margin, but can still fulfill the requirement at the system level specifications. And also meanwhile, we have new generation emerging components like wide bandgap devices, new capacitor technologies, or new magnetic materials and so on. So those are still lack of models and standards for us to do the reliability analysis. And we have already shown this, this modeling step. We say this is a modular approach that we implemented in this design for reliability and robustness software. But if we look at those steps specifically, we know that there are different stressors like thermal, humidity, electrical stress, and so on. So those multiple stressors, they have coupling, mutual coupling among each other. So the modeling extremely challenged, especially when we talk about the thermal and humidity aspect modeling. So this is a challenge that still need a lot of work to do. And also the modeling is from system to component to the system. So if we look at, okay, power device or capacitors, just look at individual components, it may be easier to model. But if you look at the system, when we integrate them together into a cabinet or into a system with a certain architecture, they themselves have strong coupling with each other. So this is we still need much more efforts to do the modeling, to build up the modeling. Another important and very important great challenges is about the testing. If we perform efficiency testing, for example, to prove that this converter can achieve 95% efficiency, it will take very little time. So we test it under different conditions. But if you want to prove that this converter can operate for 10 years with a maximum of 1% failure or 10% failure, how we can prove that? So this takes a lot, much longer time. Also, we need intensive resource in terms of time, in terms of testing samples, and so that we can validate some of our assumptions. And also, so in order to do this, to reduce the testing time, because this is a critical factor affecting the time to market of the products. So we really need new testing methods that can reduce the testing time. Also, meanwhile, we need to testing method that can emulate more closely the realistic operating conditions. So that is, as one of the examples we've shown, it's more application-oriented testing methods that for certain, at least within a certain industry sectors. So nowadays we have different testing standards. Some of them are quite general. Of course, they can offer us good information like to benchmark the products across different industries. But if we want to really understand the reliability performance so that we can provide a better service to the customers, we may need the testing method that can emulate the realistic operating condition more. Here's one example about the testing facilities we're building up since last year. As I mentioned, this is the National Power Electronics Reliability Testing Center. In this center, you can see, I will not go to the details. You can search the website, information in the website. So you can see here, we have, in the system level, we have a lot of, we call mission profile emulators for different applications. So the aim of those is to develop testing systems that can emulate the realistic operating conditions, of course, at a certain acceleration level. And after those testings, we need different testing equipment to do the parameter calculations and post-failure analysis of this. The last challenge I would like to share with us is about the scalability. So we know that power electronics are more and more used in small-scale power systems, or even our whole entire power systems. So we have done a lot of research in the component and power converters, and how those approach can be applied into the system level, into the power system level. At the moment, we're running a big project on this topic. So we try to look at the scalability, and also we try to look at the effect of the different tolerance and parameter uncertainties in the chain of the system. So what are the effect of those systems for that? Okay, I think that is pretty much what I would like to discuss together with us in this seminar. We discussed three parts. The first part is talking about why we have to look at the power electronics reliability and what are the application demands and application perspective challenges. And then we have shown line research examples for that. And finally, we have discussed the challenges for the future from the research perspective. Okay, thank you very much for your attention. And I'll be very happy to discuss with us if you have any further questions on this webinar. Thank you very much.
Okay, thank you, Professor Wang, for these explanations so far. A lot of insight, I think, on the development side, but also to the latest applications in the industry that you're actually researching for. At the moment, we had actually two questions we would like to share with you. So I will just share my screen here. So you can go to these and maybe answer those quickly. Choose the right one. There you go. Okay, so question number one we had, I just read it very quickly. It's about VFD storing. And the question basically is it correct? Let me read the whole thing. The storing VFD for a long time, maybe over 10 years, for instance, as a spare part, some of the components will decay. Capacitors will dry out, for example, and hence cause short circuits when putting it into service. Question very simply, is that correct, or does it apply to some of the older versions of VFDs?
Yeah, thank you for the questions. Yes, it is correct because if we look at data sheet of capacitors, like here mentioned, the capacitors, and we do see that there is a storage life of capacitor. That means you don't apply any electrical stress, and then you just store the capacitors in the room, and then it will degrade.
Okay, thank you very much. More questions coming. Okay, I think I hope this is answered sufficiently. So we may go on to other questions. We have still others going on, which we may just read out. First, we come to this one. I think it also has been partly answered during your presentation because this question came a bit earlier. So the question is, what is the relation between reliability and robustness?
Yeah, I think reliability is, by definition, is a probability that an item can perform its function at a certain condition within a certain period of time. So it's a probability. Robustness covers every aspect of interest. For example, if you robustness is a margin. Of course, there is a figure merit. It's a margin like between your design specification and the real capability of your system. For example, if you talk about the efficiency, and then your target efficiency is 95%, and then if you have a actual efficiency is 96%, so you have a certain margin for that. This is a robustness. Or if your voltage capability, your designed voltage capability is 400 volts, and your actual voltage capability is 440 volts. So you have 10% this margin. So this is related to reliability, robustness. Of course, the reliability or the lifetime also have a certain margin. If you say your designed lifetime is 10 years, within this 10 years, the maximum allowable failure is 10%. And then your actual predicted lifetime or design lifetime is 11 years. So this 1 year, this difference is kind of robustness, it's kind of margin. So that's why the robustness is more comprehensive. You can calculate robustness of any performance factors of interest or any parameters of interest for that. So reliability aspect, robustness is part of the robustness for that.
Okay.
Yeah.
Thank you very much. We actually have still some questions coming in, so we will not have the possibility to show them on the screen. So let me just read them out. Okay, so here's a question from Jagabar Satik. Is it correct to do reliability based on circuit topology?
It is, let me check. It is in the Q&A or chat?
Q&A, yes, you can read the questions. Or everybody, actually, if you want to read the questions, please open up the Q&A.
Is it correct to do reliability based on circuit topology? If I understood correctly, the question is it correctly to do the reliability prediction based on the circuit topology? If this is the case, the reliability prediction needs two aspects of information. The first is about the inherent capability of the components used in the system. And the second is about the operation and environmental conditions. We need both aspects of information. And then the wear out of the components will depend on certain stressors, like your voltage, like your temperature, or your humidity levels, or your mechanical stress levels, and so on. If we want to get accurate or relatively more realistic estimation, and then we need to do those kind of models to get, okay, what is the hotspot temperature of the capacitor and what is the junction temperature of the IGBT modules. And in order to obtain those informations, we do need the information of the circuit topology and the control method. because the circuit topology and control methods will affect the thermal stress, the voltage stress of those components we are interested of. This means the reliability prediction cannot only based on just like how many number of capacitors or how many number of IGBT modules are used. But as I mentioned, this quite depends on your requirement if you want to get more realistic estimation. But if you want just get a very, very rough preliminary prediction to benchmark different choice of components or different technologies, and you don't have the details, you don't have the detailed models of your circuit, you don't have the specific lifetime models of your components, and then you based on the some handbooks, you count the part numbers. You say you have 10 IGBTs, you have 5 capacitors in this operation, and then you can calculate the failure rate. But from our perspective, in order to get a better, more realistic estimation, we need to base on the circuit topology and also the control strategies of the converters. This is where we need both the power electronic designers and the reliability engineers work closely with each other to do the analysis for that. I hope this answers your question.
Okay, thank you very much for the in-depth answer. We do actually, I see that we have at least one more question in the Q&A. We also have received some questions in the chat function. Now, we may just pick up one more question, which is directly to your, in regards to your presentation from the chat before we go on to the selected questions.
Yeah.
This question is from, is in the chat actually from Mr. Yuri Podraj, if I say this correctly. Coming to the question, how and which parameters you measure in order to monitor DUT health on slide 17?
Okay, first, let me go back to 17.
Maybe we can share back the screen on.
Yeah. Yeah, in this case study, we monitor the unstable voltage of the IGBTs.
Professor Wang, could you take back the screen so we can see the slide?
Yes, sure.
Thank you.
Can you see the screen now? Yeah, so now let's back to this slide 17. In this example, we measure the unstable voltage of these IGBT modules and the diode. The unstable voltage means when the IGBT switch is on, and then there is a low voltage drop across these two terminals. This voltage usually in the range of like 2 to 4 volts. With the degradation of the IGBT, this voltage is increasing. And also we measure the forward voltage of this diode. That is also when the diode is conducting. There is a low voltage between like 2 to 4 volts. We measure this voltage, and then we see how this voltage value is developed along the testing. Usually this voltage is increasing with the testing, with the degradation level. And here we show that this delta V means the change of this voltage. We can see at the beginning, the change is quite insignificant. It's almost close to zero. And then after a certain point, you can see it's increasing with a higher slope. So this is an indication that it close to the end of life. But here we can see that the delta V here is actually quite low. It's talking about this is the millivolt. That means we need to identify the change in the scale of millivolts from a few volts in the on state. But also don't forget that when the switch is in the off state, it's turned off, there is a voltage that could up to the rated voltage of this switch. In this case, it's up to 1.7 kilovolts. So we need to identify this, a small change, a tiny change out of this 1.7 kilovolts stress. So this requires us to use a certain measurement circuit. That is what we discussed in the last example. So the widely used solution is that we add a circuit across these two terminals of the switch, and then we block the high voltage. We only let the low voltage pass through, and we can measure this small change in the millivolt range with high accuracy, so that we can detect the degradation of the power semiconductor devices.
Okay, thank you very much, Professor Wang. Thank you for that answer. I know we have some questions left in the channel, in the chat, but also in the Q&A section. We will follow up these questions, answer those via email that you have registered with, and then send these out and share this with you. For time reasons, I would now like to go on with the selected questions that we had also prior to the session. So maybe we could go on to this part and go a few of these. Thank you.
Yes, thank you. There are a few selected questions before this seminar, so we're going through it together. I think the first question is related to this power analyzer from Hilke, the featured FFT function and harmonics analysis. So the question is, what are the main applications and what are the benefits and features of the FFT analysis comes with this power analyzer? First of all, I would say the FFT function and harmonic analysis becomes more and more important. As we discussed at the beginning of this webinar, that because power electronics converters are increasingly used in our existing systems, but power electronics itself, converter itself, is a nonlinear characteristics because there is high frequency switching of the semiconductors. So this switching process will induce the harmonics. If there's only a low percentage of electricity processed by power converters, it may not do harm to our bigger system. But nowadays, there are more and more power electronics converters that are interfaced in our system, like renewable energy generations, EV charger, and so on. All of these will induce the harmonics into our system. So these harmonics, if not dealt with properly, it will circulate in the system. It will do harm to some other systems as well. So that's why the first step is that we can model these harmonics, and then we can measure. The next step is we can measure these harmonics. We can do the FFT analysis to do the harmonics analysis. And the third step would be, okay, we can find ways to mitigate or reduce those harmonics. So that's why the FFT function and harmonic analysis itself will become more important for those reasons. And then if we look at this power analyzer specifically, just from our perspective, just personal perspective, is that we could see this power analyzer can offer a broadband harmonic analysis because of this the frequency range, because of this together with this current sensors and so on, and the phase compensation. So we can do a broadband harmonic analysis, which brings additional capability. So this especially relevant to maybe to the future applications where we have power converters with the switching frequency much higher than what we did today. When we apply like silicon carbide device or GaN device, the switching frequency is increased. And then if we want to understand the harmonics related to those switching frequency, and then we need increase or extend the capability, the bandwidth of the analyzers. So this is the first question. And then the second question is about the pros and cons of high bandwidth. In this way, the comments is a higher the measured and tracked bandwidth is a more environmental influence. You may capture these values are not from the DOT, but from the surroundings. And our harmonics up to the fifth order, 500 orders, are really suitable to get accurate measurement results. First of all, I fully agree that the comments here, there is a challenge that if we measure those voltage and current signals at high frequency, the effect, the parasitics of your sensors and probes becomes relevant. So there is a chance that the capture signal, those noise come from your measurement system, from your probes or from your sensors. Of course, there is this research going on to get more accurate measurements at high frequency and so on. The progress are going on for that to deal with the parasitics of those probes and sensors. So that's why the effect of this generally depends on how the measurement are conducted, the sensors and probes. It depends on the development. If we can have new types of sensors or probes that has extremely low parasitics and also good noise immunity, and in this way we're still capable of doing accurate measurement even at higher frequency for that. Harmonics up to 500 orders of the fundamental frequency are really suitable to get the accurate measurement results. If I understood correctly, this the fundamental frequency talking about here is like 50 hertz or 60 hertz. So this talking about 25 kilohertz to 30 kilohertz. The accuracy will depend on the measurement, the sensors and probes, but whether it is necessary to get those results. This depends on the applications or the purpose. Like if for the R&D purpose, if we want to get a better estimation at this frequency range, we do need this capability. But I mentioned this relates on the development on the front end hardwares, and also could also be the software analysis to try to reduce the effect of those noise after we collect the data for that. This is the second question. And then the third question is the COP is expectedly going to play an important role in establishing international standards which regulate power reliability and its evaluation methods for power electronics components. Would you disclose some examples of subjects which should be regulated with higher priority? Here, I would like to give a few examples of the subjects that, just from our perspective, that may be worthwhile to have standards on it. The first one is the testing for emerging power electronic components like silicon carbide. And again, I know there are different organizations are working on this to put up the testing standards. So how we do perform the power cycling testing, and what are the relevant health indicators for silicon carbide, and again, what are the different type of reliability aspect testing that need to perform. So there are several organizations are preparing for this. This is very good. And the second aspect is about what we call application-oriented testing. Of course, this would depends on this will talk about the specific industry sectors. So for specific industry sectors, put up application-oriented testing, for example, the mission profile-based testing, to look at the representative mission profiles, and then to perform the accelerated testing based on that, instead of a static testing point. So this is the second aspect of example. The third one is about the mission profile itself. So the mission profile is the long-term operational and environmental conditions of the system. Like for example, in the automotive industry, we have these driving cycles. like 20 minutes, 30 minutes driving cycles. So these driving cycles can use to benchmark the performance of cars or the consumptions of the cars. Similarity, like in wind industry, we have this three class of wind profile with low wind speed, medium wind speed, and high wind speed. So those are representative emission profiles, are very important to benchmark the products across a specific industry sector. But there are also some other areas like PV or even traction. As far as we know, there are not there is no such representative emission profiles. If we can have some standard on those emission profiles, and then it will help us to benchmark the products to validate the products. The fourth one is about the end-of-life criteria, lifetime definition, confidence level for specific industry sectors. So this is actually a part that we often overlooked. For example, if you read the data sheet, the lifetime of this capacitor is 5,000 hours at 85 degree at 400 volts, the rated voltage, and rated ripple current. But what does it mean of these 5,000 hours? Does it mean that if you buy, let's say, if you buy 1 million capacitors, does it mean all of these 1 million capacitors can survive for 5,000 hours? And then, or does it mean after 5,000 hours, all of the capacitors will fail? The actual case is that it's neither of these two cases. So within these 5,000 hours, there will be a certain number of capacitors fail. But how much of that? And how we define the failure of a capacitor. Usually, like we say, we have a capacitance drop, like for electronic capacitor, 20% capacitance drop, or dissipation factor increased to 3 times, and so on. So those are kind of end-of-life criteria. But then when we talk about 5,000 hours, we actually don't know within 5,000 hours how many capacitors will fail if you buy 1 million. So this is related to lifetime definition. So lifetime is usually defined at a certain reliability level. Let's say if we defined at reliability level of 0.99, this is the time when the reliability dropped to 0.99, or it means when there is 1% accumulated failure for that. This means if the lifetime is defined at 1% failure, this means within 5,000 hours, there is 1% of this 1 million population of capacitors will fail. The third is the confidence. That is related to how confident you can say so. What is it? So how confident you can say so that within 5,000 hours there is 1% failure, because your data, your models are derived from testing or fit operation. So those are from small samples. Now you want to use the conclusion from those small number of samples to represent this type of capacitors. There is uncertainty that is described by confidence level. Whether you have confidence level of 90%, this means statistically you are 90% sure that within 5,000 hours, you will have maximum accumulated failure of 1%. Or you have 10% risk that within 5,000 hours, there will be more than 1% failure. So in this case, you know exactly the risk for your system. But those kind of information, for some components, they are well-defined, but for some components, they are not well-defined. And usually those information are not provided in the datasheet or in the application note. But those information are very critical, very important. If we don't know them, and then we have no chance to understand the real risk. So the fourth question is about the oscilloscopes and power analyzers, and when do you use power analyzer, when do you use oscilloscope? I think the power analyzer features with higher precision because of the bit of the ADC is much higher than the oscilloscope for the dominant products in the market. So it is suitable for the high precision measurement. An oscilloscope is good for the fast measurement. The resolution is high, but then the ADC, maybe 12-bit, 8-bit, 10-bit, so they're different products. So there's somehow a trade-off between this accuracy of the ADC and the sampling speed. For us, we usually use a power analyzer to measure the efficiency, to get more accurate measurement of the voltage and current, and to measure the power, harmonics, THD. For the oscilloscope, we use to measure the switching transition to get the power loss, the switching loss of the switch, because the switching transition is very fast. It's from the nanosecond to sub-microsecond level, or to do the proof of concept verifications, just to get a rough idea whether the waveforms is what we look like, what we expected, and so on. The last question, I think, is a combination of this Hioki power analyzer and current sensors. I think this is the second from the last, and now to realize the original function called phase compensation technology. So what do you think about these ideas, so to speak, philosophy? First of all, for us, I think this function is highly valuable for scenarios when the power factor is close to 0 at high frequency. This like inductor, magnetic components, or capacitors characterization, because those are either inductive components or capacitive components. The reason is because if we have a power factor close to 0, that means almost the reactive power, and then the active power is extremely low. In this case, if we have a certain level of the phase difference, we can see that there is a large error in the active power, compared to the case where the power factor is close to 1, and then the error will be much less. So this is the reason why we have one of these power analyzer to use it for this high frequency or medium frequency transformer characterization. As an example 6 we discussed, because these magnetic components, their power factor is close to 0. So the difference, the phase difference between the voltage and current is close to 90 degrees for that. But of course, the application are not limited to like inductive component characterization as we did. The last question, which software do you use to analyze and measure data in your research? In our research, our students mainly use MATLAB to do the data analysis. They develop some program or use an existing toolbox from MATLAB, or they use for the reliability analysis, data analysis. We also use ReliSoft. This is a reliability data analysis software, or Militab. For some of the equipment, of course, some equipment supplier they have their customized software. So if in that case we prefer to use the software that already developed by the supplier. We also use some self-developed software tool like mission profile data analysis. We developed the software tool by ourselves to do the analysis. I think that's all of the selected questions to discuss.
Yes, thank you very much. So maybe we can go on to our last slide. So thank
you very much.
Professor Wang, I think there's a lot of things to take away from your presentation. As I said, like from the beginning, the basics of why power electronics is becoming increasingly important for industry applications, and a lot of applications around, explanations around this, what is actually done and what we can expect in the future in these fields. So, and also, yeah, for going over our questions, which were, I think, a bit, well, very specific at some point. So thanks a lot for all this. I think everybody, I hope everybody enjoyed this webinar and could take away some aspects for their future projects. The questions remaining, as announced, we want to follow up and we'll answer those to you in an email. Okay, so we also will share the webinar documents and see the presentation later on. We will send out some download links and to share these materials and follow up with these questions. So thank you very much for attending these almost 1.5 hours. Thank you very much, Professor Wang, for your explanations, and we hope to see you soon again.
You're welcome. Thank you everyone for attending this.